Okay, so now let's look at some of the math problems in the relationship between advertised window and the sequence number space. So here we are going to design a transport layer protocol like TCP. So it has to be reliable byte stream based protocol using sliding window approach. And the bandwidth of the network is 100 megabits per second. The RTT is 100 milliseconds. The maximum segment lifetime is 60 seconds. So given all these things, we want to find out design the transport layer header basically, where the number of bits for the sequence number space and the advertised window needs to be found. Okay, so now first let's do the advertised window based thing. To keep the pipe full, the number of bits that are needed for the advertised window is uh, depends on the RTT bandwidth product, because we know to keep the pipe full, the advertised window has to be equal to the RTT bandwidth product, right? That's what we saw in this previous topic. To keep the pipe full, we have to send as much as possible, um, and what we can send depends on the bandwidth, and we want to send for the entire round trip time till we get an acknowledgement. So and the receiver has to be able to accept all those bytes. So the advertised window size has to be equal to the RTT bandwidth product. So if you want to now find the number of bits you need to use to advertise that advertised window size, then it has to be logarithm of the RTT bandwidth product to the base 2. So that's why we are going to now substitute the RTT value, which is 100 milliseconds. The bandwidth is 100 megabits per second. So this is 100 milliseconds. I'm converting that to seconds, and then 100 megabits per second. So I'm dividing by 8 that 100 to convert that to bytes per second. So if we now do the math, um, so 100 milliseconds times 100 megabits per second is now 100 times 10 to the negative 3 seconds, then 100 times 10 to the 6 bits per second. Now I'm doing like this here, seconds and seconds cancel out. So this is 100. Now this 10 to the negative 3 and 10 to the 6 can be is going to be this 1000. So this 100 times this 100 times this 1000 bits, and I'm dividing this 1000 bits by 8 to convert to bytes. So I should not have seconds here because I already cancelled the seconds. So this is 1000 bits divided by 8 is going to be bytes. So this is 1000 times 100 times 100. So this is 1000 over 8 is 125. So 125 0000 bytes. So this is actually my advertised window size. So these many bytes I can store in my buffer, and that's what I can advertise. Okay. Now I need to know how many bits I need to use to represent this value, 125 times 10 to the 4. So the way we do that is we will have to do the logarithm of 125,000 to the base 2. Okay, so that's going to be logarithm of 125,000 to the base 10 divided by logarithm of 2 to the base 10. Okay, so logarithm of 125,000 is going to be this divided by logarithm of 2 to the base 10. So I'm using the base 10 log. So I'm getting 20.25, and if I take a seal, that's going to be 21 bits. So that's what I have here. Okay. Now we know also that from the theorem, the number of from the theorem, what we know, the advertised window size has to be at most sequence number, range or space, both are same, half of the sequence number space. So which means my sequence number space is twice the advertised window size. Okay. Now, of course, greater than at most twice. At least sequence number space has to be at least twice the advertised window size. Now, again, we want to use only the required number of bits, so we don't want to go what is required beyond what is based on advertised window size. So we'll say the sequence number space is twice the advertised window size. Okay, so which means our advertised window size is this 125.0000, so that's going to be 25 to 50 4 zeros, right? So I can go ahead and find the number of bits needed based on the advertised window size is going to be again log to the base 2 of this 25.040 zeros, 254 zeros. That's right, because advertised window size is 125 zeros, so twice of that is 254 zeros. So that's going to be this to the base 2. So if you again use the calculator, 250, then 4 zeros to the base 2. So I'll do the log to the base 10 and then divide by 2 log. It's going to be 21.25 now. So when I take a seal of it, that's going to be 22 bits. So the number of bits needed for what? The number of bits needed for the sequence number space based on the advertised window size is 22 bits, because the sequence number space is 2 times this. So we need to support this many bytes with unique sequence numbers if we just go by the advertised window size. Okay. Now the other part of the problem has what? The maximum segment lifetime. So in order to take that into consideration, the number of bits needed for the sequence number based on the maximum segment lifetime is the maximum segment lifetime times the bandwidth and log to the base 2. So if you do the math for that, the maximum segment lifetime is going to be 60 seconds times the bandwidth is 100 megabits per second again, so 100 divided by 8 times 10 to the power 6 bytes per second. So if you do the math for that, it is 60 seconds times 100 divided by 8 times 10 to the 6. So this. Now this to the log, then to log, that's going to be 29.48, so it's going to be 30 bits. So based on the maximum segment lifetime, it is 30 bits. Okay. Of course, then we have to take the maximum of the two, because if we use based on just advertised window, we need only 22 bits, but it's going to then wrap around quickly. So if you want to sustain till the maximum segment lifetime, based on the maximum segment lifetime, we found that we need 30 bits. So that's why we have to go with 30 bits. Okay, so we need 30 bits for the sequence number. Okay, maximum of 22 and 30, 22 based on the advertised window and 30 based on the maximum segment lifetime. Okay, so now let's go to this question. So suppose TCP operates over 1 gigabits per second link, and this is TCP itself, so we are not designing any new transport layer protocol, we are using the classical TCP. So now assuming that TCP utilizes the bandwidth continuously, the full bandwidth continuously, how long would it take for sequence numbers to wrap around completely? Okay. So which means you're using a standard TCP which uses 32-bit sequence numbers, and you're sending the bytes one after the other. That's what it means by the statement that you're utilizing the full bandwidth continuously. So so you're sending, say, starting with byte 0, then byte 1, and so on. It'll go all the way to 2 to the 32 minus 1. Then you have to come back to 0. So we need to know how long it takes to wrap around. Okay, so the bandwidth is given to be 1 gigabits per second, so which is of course 1 times 10 to the 9 bits per second. And now I want to get it in bytes, so I have 1000 times 10 to the 6, so I'm dividing the 1000 by 8 to get it in bytes. So it is 125 times 10 to the 6 bytes per second. So essentially I can send 125 times 10 to the 6 bytes in 1 second. And so I have to now find how long it takes to send 2 to the 32 bytes, because that's what is allowed by a sequence number. It's a 32-bit sequence number field in the TCP header. So you can send this many bytes in 1 second, 125 times 10 to the 6 bytes in 1 second. So how long it takes to send 2 to the 32 bytes? That's going to be 2 to the 32 divided by this 125 times 10 to the 6 bytes per second. So that's going to be 34.36 seconds. So which means after this 34.36 seconds, if you send one more byte, that byte is going to have a sequence number of some other byte that has been sent earlier within this 34.36 seconds. Basically, that's what this wraparound is. So to send from 0, 1, 2 up to 2 to the 32 minus 1, all these 2 to the 32 bytes, it took you 34.3 seconds. So if you send again a byte, that's going to have the sequence number in this previous range. Okay, so that's what is characteristic of this maximum segment lifetime. So obviously it is small, so we need to be able to use timestamps. That's why we use the timestamp option. So suppose, let's say we have used a timestamp option, and it's a 32-bit option, let's say, and it increments 1000 times during the wraparound time we have found above. Okay, what it means is during this 34.36 seconds, the timestamp value that you use in the options has changed from one value to the other. So it has changed 1000 times. Okay, so what we want to find out is the new maximum segment lifetime that we can have, or basically now how long it takes now for the timestamp to wrap around. Okay, so the timestamp again is 32 bits, right? So because of the timestamp wraparound, that's the maximum segment lifetime now, because then you will have the same timestamp and the same kind of 32-bit byte number. So that's a wraparound, right? So let's do this. So the timestamp increments 1000 times within 34.36 seconds, right? So the let's do it like this. So let me call epoch 1, which is 34.3 seconds, for during which the sequence number goes from 0, 1, 2 all the way to 2 to the 32 minus 1, and then another epoch which is again 34.36 seconds. Again it goes from 0, 1, 2 up to 2 to the 32 minus 1. Oops. Okay, so and so on, it continues like that. So for another epoch, it does the same thing. Okay, now the timestamp during one epoch, during the wraparound time that we found above, that's what the problem statement tells, right? Suppose and that 32-bit timestamp field increments 1000 times during the wraparound time we found above. So within this time, timestamp field increments 1000 times. So let's say the timestamp was initially 0, it has incremented 1000 times, so its value would be then finally. So if it increments once, it is 1, if it increments twice, it is 2, and so if it increments 1000 times, it is 1000. So the beginning of the next epoch, its value is 1000, and it's incremented 1000 times, so its value will be 2000. And the third epoch, it would begin with 2000 and it will go to 3000. So it will keep on keep incrementing like this until this value hits what, 2 to the 32, this it hits this, because the timestamp is a 32-bit field, so timestamp will also eventually hit sometime this 2 to the 32 minus 1, right, and then wrap around. So we need to basically find how many epochs it takes for the timestamp to wrap around now, right? So it's 2 to the 32 divided by 1000, because for every epoch it increments by 1000, right? So and it can go up to 2 to the 32, the maximum value for the timestamp. So 2 to 32 minus 1, but it starts with 0, so the range is 2 to the 32. So that divided by 1000 is going to give you the number of epochs that will take for the timestamp to wrap around. Okay, because epoch 1 it increments by 1000, epoch 2 another 1000, so 2000, epoch 3 now 3000, epoch 4 4000, and so on. So how many epochs it takes to hit 2 to the 32? 2 to the 32 divided by 1000. So, and each epoch is how much? Each epoch is of duration 34.36 seconds. Okay, so if you do this math now, 2 to the 32 divided by 1000 times 34.36, so that's going to be these many seconds. Okay, so this many seconds. Now I want to get it in years. Let's say how many seconds is in a year. 1 year is 365 days, and each day is 24 hours, and each hour is 3600 seconds. So I need to divide that number by this 365 divided by 24 divided by 3600. So it takes 4.68 years for the timestamp to wrap around. Okay, so that could be your maximum segment lifetime. So if you use a 32-bit timestamp that increments 1000 times within the maximum segment lifetime, then you can have 4.68 years of the maximum segment lifetime. Okay, alright, so let's move on to this problem now. So we have here TCP that implements an extension for the advertised window. Okay, so using the options field basically, so that it can advertise more than 64 kilobytes. So let's say we're using such an extended TCP or a 1 gigabits per second link means network, and the latency of the network is 100 milliseconds. By latency we mean here the round trip time, and we want to transfer a 10 megabyte file over this link. Okay, and the TCP receive window size of the receiver is 1 megabyte. Okay, and if the sender sends 1 kilobyte packets, and we are kind of neglecting congestion here and also assuming that no packets are lost, we want to find out several things. First is how many round trip times it takes until the congestion control algorithm that is used is slow start, and so basically we want to find out how many round trip times it takes for slow start to reach this 1 megabyte. Now let me go over the question again. So we have the bandwidth given to be I worked it out here, but let me see. Let me write some more thing here so that it's easy to follow. So the bandwidth is given to be 1 gigabits per second. Then the round trip time is given to, the round trip time is 100 milliseconds, Now what is of importance first is the TCP receive window size, which is given to be 1 megabyte. Now that's actually our advertised window size, because you cannot advertise more than your receiver window size, the receiver buffer space, right? So this is our advertised window size, and we use here the slow start condition control algorithm, and the size of each data packet size is going to be 1 kilobyte. So each packet that you send is 1 kilobyte size, and using slow start. Now, as the problem also said, there's no congestion, so which means here the effective window size is going to be decided eventually, or is kind of is bounded above by the advertised window size, because eventually so you will start with 1 kilobyte of packet, then you double it and then double it and so on, do this exponential increase, but you cannot go beyond the advertised window size. Okay, so that's what I show here. You do start slow start, which means you send in the first round trip time 1 kilobyte, then the second round trip time you double this, which is 2 kilobytes, so you send basically 2 packets. Then in the third round trip time you send 4 packets, then the fourth round trip time you send 8 packets, and so on. So we need to find how many round trip times it takes to hit 1 megabyte. 1 megabyte is how many kilobytes? 1024 kilobytes. So you're increasing 1, 2, 4, 8, then 16, 32, and so on, right? So as you see here, this is a kind of a binary relationship. So 8 is 2 to the 3, right? Now the number of round trip times is 1 more than the exponent. So 10 to the 24 is 2 to the 10. The number of round trip times is 1 more than the exponent. Okay, again, so 8, so you see here 8 here is 2 to the 3, but the number of round trip times is 4, 1 more than 3, right? Similarly, 4 is 2 square, 2 raised to 2, and the number of round trip times is 1 more than 2, right? So like that, 1024 is 2 to the 10, and the number of round trip times is 1 more than 10, which is 11. Okay, so it takes 11 round trip times for the slow start as you increase the condition window size, and eventually the effective window size also increases based on the condition window size. So it takes 11 round trip times for you to hit the advertised window size, which is 1 megabyte. So once you hit the advertised window size, you cannot go beyond that. So that is something like this. So you have been sending in this round trip times, and so you have been increasing like this exponentially, 1, 2, 4, 8, and so on, 16, and now you have hit this advertised window size, which is 1 kilobyte, sorry, 1 megabyte, right? So you have hit this 1 megabyte, which is 1024 kilobyte, and you have increased like 1, 2, 4, and so on, and it took you, and if say this is your round trip times, okay, this is your round trip time, it took us how many round trip times to reach this 1024 kilobytes? It took us 11 round trip times. Okay, so the first round trip time is sent 1 kilobyte, second round trip time is sent 2, then 4, 8, and so on. It took us 11 round trip times to get to 1024 kilobytes, and then the 12th round trip time you send another 1024 kilobyte. The 13th round trip time you send again another 1024 kilobyte. Okay, Okay, so now, so you keep sending like this until you want to send the entire file, right? So now we want to find out, the second stage of the problem is how many round trip times it takes to complete sending the entire file. Because the way we have sent is, as I think I show here. Now let me put it here. So we have sent 1 kilobyte, then 2 kilobyte, 4 kilobyte, and so on up to 1024 kilobytes. So all of this have been sent in 11 RTTs, right? So these things have been sent in 11 RTTs, the whole thing. And then you have some more RTTs, right? Let's say some X number of RTTs, and in each such RTT we are sending 1024 kilobytes, right? So up to 11 RTTs we have a variable number of effective window size, because this was based on our congestion window size. Okay, and from now on this is going to be based on the advertised window size, because until this point is based on the congestion window size. That's what is this. It took 11 RTTs, and now this whole thing is based on the advertised window size, and in each RTT we are sending 1024 kilobytes. Now everything put together should be equal to the file size, and the file size is given to be 10 megabyte. So 10 megabyte is nothing but 10 times 1024 kilobyte. Then 1 megabyte is 1024 kilobytes. So let me make sure it is 10 megabyte. Yeah, it's a 10 megabyte file. So that's going to be 10 times 1024 kilobytes. So essentially that's going to be 10240 kilobyte, right? Because everything is in kilobyte here. So essentially we want to add up this plus x times 1024 is equal to 10240 kilobytes. So the only unknown is x, but we have to first find this summation and then subtract and then divide by 1024. So that's what I'm going to do now. Let me create a new one. Okay, so what we could do is, now we need to know how to do this exponential, this is arithmetic progression, right? No, this is not a geometric actually, but yeah, so the common term is going to be 2 to the 0, or 2, right? 2 is increasing exponents of 2, 1 is 2 to the 0, 2 to the 1, then 2 squared, 2 cube, up to 2 to the 10. So 2 to the 0 plus 2 to the 1 plus 2 squared, 2 cube, up to 2 to the 10 is going to be 2 to the 11 minus 1 divided by 2 minus 1. Okay, and so this is a geometric series. So 2 to the 0, 2 to the 1, 2 square up to 2 to the 10 is 1 more than this exponent, which is 2 to the 11 minus 1 divided by the common base is 2, so 2 minus 1. So that's going to give you 2 to the 11 is 2048, 2048 minus 1 is 2047 divided by 1, so that is 2047. So essentially what we are going to do is, we are going to, I think I have it here. So we are going to subtract 10240 minus 2047. Again, why is that? Because so this is 10240 and this is going to be 2047. That's what we found now. So 2047 plus this x times 10 to 1024 is going to be 10240. So x times 10240 is going to be 1024 t minus this 2047. So that's going to be 8193, and that divided by 1024 is going to be 8 point something, 8093, and x is going to be 8.0009 or something like that, right? How many zeros are here? 3 zeros. Okay, so still, so what this means, this many RTTs, right? So the number of RTTs we need after the 11th RTT is going to be 8.0009 RTTs. Now you have to be careful here, you have to round it to an integer value because the number of RTTs is an integer. We cannot say it is 8 RTTs because it takes something little more than 8 RTTs, right? So that's why we have to round it or seal it basically and say it is 9 RTTs. Okay, so that this is where to be careful. So this is what we sent in 11 RTTs. The first RTT is sent 1 kilobyte, second RTT is sent 2 kilobyte, third RTT 4 kilobytes, and so on up to 1024 kilobytes. And that's what we've I said it takes 11 RTTs up to that point, and then some number of RTTs which is x, and in each such RTT we are sending 1024 kilobytes, which is based on advertised window. And this is, so put together all these things, you want to send a file, so that is 10 megabytes, which is 10 times 1024 kilobytes, so that is 10240 kilobytes. So if you add up all these things, that's what we did now, the geometric series thing, which is 2047 plus x times 1024 is 10240. So x times 1024 is 10240 minus 2047, which is 8093. So x is going to be 8093 divided by 1024, which is this. So it takes slightly more than 8. So the number of RTTs is an integer, so we have to seal it to 9 RTTs. So essentially now what it is after the 11th RTT, it takes 9 more RTTs starting from here, right? So it takes 9 more RTTs starting from here. So that's what I wanted to indicate, 9 more RTTs. So totally how many RTTs? 11 plus 9, so it is 20 RTTs. So if you look at the math, so it takes 20 RTTs totally. Now each RTT is given to be how long? Latency is 100 milliseconds. So the total delay is going to be 20 RTTs times 100 milliseconds. So 20 times 100 times 10 to the negative 3, that's going to give you 2 seconds. And so the throughput is going to be the file size that you wanted to send, which is 10 megabyte divided by the total delay, which is 2 seconds. And 10 megabytes is going to be 10 times 1024 kilobytes, and 1 kilobyte is 1024 bytes, and this is 8 bits divided by 2 seconds. That's given, that comes out to be 41.94 megabits per second, or if you round it to you can say 42 megabits per second, which is now 0.042 gigabits per second. So why I converted to gigabits per second, the bandwidth of the channel or the link is going to be in gigabits per second, which is 1. So this is what is the throughput, and the bandwidth is 1 gigabits per second. So the efficiency of the link utilization is here throughput divided by the channel bandwidth, which is throughput is 0.042 and the bandwidth is 1, so it is just 4.2%. So if you look back at this, you see here now the bandwidth is not used efficiently at all. It's just 4% of usage. Now the reason for that is because it is bounded by the advertised window size, because you could, there's no congestion, so you could keep increasing, and the network has 1 gigabits per second of bandwidth, so it would not drop packets. So the limitation here was the advertised window size. Okay, so that's why we cannot send more than this 1 megabyte and 24 kilobytes within a round trip time after the 11th round trip time. Okay, so that's the problem.